Okay, so in this first question on rates of reaction, we're looking at a chemical reaction, the rate of a chemical reaction between two reactants, one of which is a solution and the other one which is a solid. So it could be magnesium and hydrochloric acid, for example, which is in the next question. So it's asking us just for four statements and is asking us to identify which one is not going to cause the rate of a chemical reaction to increase. And so what we need to be looking at here is two possible situations. One is situations where we increase the frequency of the collisions. The second is where we can affect the number of particles with the activation energy potentially. So going down the list, the first one, increasing the concentration of the solutions is going to increase the number of particles within a fixed volume. And so that's going to increase the number of collisions as a result. So that isn't going to be one of the potentials. Heating the reaction mixture is going to make particles move faster and hence allow them to have more collisions. It may also allow them to have more likelihood of having the activation energy. And the last one, grinding the solid so that it forms a fine powder, is going to increase the surface area of the substance. And so we can assume from that that that's going to increase the rate of reaction also by allowing more collisions between, in our example, we were using the hydrochloric acid and subsequently a magnesium powder, for example. So that's also not the answer. The correct answer then is obviously the one which is remaining, but this is because increasing the volume of a solution, but importantly keeping the concentration the same, keeps the number of particles per volume the same, i.e. it keeps the distance between the particles the same, and so that doesn't affect the number of potential collisions per second. If those collisions were to have occurred, then question 2 is then asking us, what is the minimum amount of energy which the particles must have if they are to react? And we see this on energy diagrams whereby it's given the abbreviation EA, but that is also known, obviously its correct name is the activation energy. And by the use of a catalyst to a reaction mixture without changing anything else, this also causes the rate of reaction to increase, and this is because this allows the activation energy to be decreased. Okay, and this decreasing of the activation energy allows a greater likelihood of particles, when they do collide, to have that activation energy if that energy barrier has been reduced. So bringing all of that together then, we've got a graph here which shows mass loss from a reaction vessel. So it's something which is generating a gas, and obviously the gas particles are leaving the reaction vessel, and we're just recording the mass as that then decreases over time. And three different reaction conditions. The first one is asking us, so production of the most product. Because we've lost mass on the y-axis, we can assume that the mass loss is one of the products, and so the one with the greatest mass loss is the one which is going to the highest point, so that's C. The one which finishes first is the one which gets to a gradient of 0 first, and so C finishes roughly there, roughly around the same point as A. To be fair, well, that intersects A and B's line, but B appears to have finished off in roughly half the time of A and C. That gradient has started to go horizontal at that point there, and so that has finished off a lot further and faster than reactions A and C. And the one which has started the slowest rate is the one which is going up with the least or least steep gradient, and so B and C, have gone off with a gradient vaguely like that. If we just compare that to A's potential gradient at its initial rate there, we have A with a much slower gradient with less steep gradient, and so A is the one which is going off at the slowest rate.